Hi, everyone. It's our pleasure to have with us today Tom Hutchcroft. He's from the University of Cambridge. Tom received he's one of the two recipients of the 2019 Roto-Davidson Prize. And the prize announcement said that was in recognition of his many beautiful results in probability theory, including on random and self-avoiding walks, random forests, and percolation theory. He's going to talk to us today, give us a talk today about phase transitions and hyperbolic spaces. So take it away, Tom.
Thank you. Thanks for the introduction. I'm very grateful for the opportunity to be here speaking to you all today. It's been very nice meeting some of you this morning. I look forward to meeting more of you this afternoon. So I'm going to be talking about phase transitions in hyperbolic spaces. So let me just start, first of all, by saying, what do I mean by a phase transition? Well, this will be familiar to many of you. All I mean by this is I have some kind of large system that has many microscopic constituents, and these microscopic pieces of the system are described by some parameters that I'm free to vary continuously. And a phase transition occurs when I vary these continuous parameters by some small amount through a special value, and I see some kind of abrupt or perhaps even discontinuous change in the behavior of the system at the macroscopic level. Okay, so of course, we're all familiar with things like the solid, liquid, gas phase transitions from our everyday lives, but there are many other systems that undergo phase transitions. In fact, it's almost the generic behavior. If you have a large complex system, it almost always undergoes some sort of phase transition. In nature, we also see things like in magnetism, there's a phase transition at the Curie point that's described by the Ising model, or for a non-physical example, you could look at the computational complexity of average case optimization problems with random inputs, where there's also lots of extremely interesting work on phase transitions there. And, you know, this is something that is often very hard to understand theoretically, although there's a huge amount and growing amount of work on it. Okay. Now, it turns out that for many systems, if we actually look at the critical point itself, so if we tune the parameter to be exactly at the point where the phase transition occurs, we see often a very rich picture with all these kind of fractal-like behaviors and things like that. So on the left here, I have a picture taken from Jason Miller's website of critical percolation in 2 dimensions. These are kind of the boundaries of the clusters. You see they have all this very delicate fractal-like structure with all these sort of fjords and things like that. Actually, you know, the solid liquid gas phase transitions as we normally observe them don't really have this kind of behavior, but many other systems do. So I'll come back to this for percolation later. And this is something that, you know, understanding critical phenomena has been, you know, a central task of sort of mathematical physics, and in particular, you know, probability theory as applied to mathematical physics over the last however many years. And these things are now quite well understood in 2 dimensions, in particular for a small set of models, they're extremely well understood, and also in high dimensions. But if you want to understand critical phenomena in 3 dimensions, things like that, this is really very poorly understood at the moment for basically every model. Okay. So the specific model I want to tell you about today is Bernoulli percolation. So in many ways, Bernoulli percolation is the simplest to define example of a system undergoing a phase transition. Of course, that doesn't mean it's the simplest to study. So all we do in percolation is we start with some graph G, which on this slide I've taken to be the square lattice, and we just choose to either independently at random, every edge is either kept with probability p, in which case we call it open, or it's deleted with probability 1 minus p, and we call it closed. And we just do this independently at random for all the different edges. And we're interested in kind of the geometry of the connections in this model. So it was originally introduced by Broadbent and Hamsey, I think, to model sort of gas masks or something like that. But anyway, you have some kind of random porous medium, and you're interested in the connections that exist between different parts of the space. Okay. Now, the first interesting thing about percolation that really sets it up to be an interesting model to study is that it does indeed undergo a phase transition. So in particular, if we define theta of P to be the probability that the origin belongs to an infinite cluster, an infinite connected components, then this is 0 at small values of P. At small values of P, there is no infinite connected component. And then for P close to 1, there is. And this is actually now known to be true on basically everything, every infinite graph, with the exception of the obvious sort of one-dimensional examples where it's not true. So as soon as you're at least two-dimensional, you have a phase transition for percolation. Okay. And in fact, for this specific example depicted here of the square grid, it's a famous theorem of Keston from the 80s that the critical probability is exactly equal to a half. Now, if you're new to percolation, though, you might get the wrong impression from this. So a warning is that, generally speaking, we shouldn't expect to be able to compute the critical probability exactly. And there's no reason for it to have any kind of nice, to be an algebraic number or anything like that. Okay. Now, once we know that a phase transition exists, there are many questions we could ask. So I want to highlight two of them. So the first is, well, can we understand what actually goes on at this phase transition? So perhaps the most basic question is, well, we know PC is the boundary point of these two phases, right? Below PC, there are no infinite clusters. Above PC, there are infinite clusters. What happens when you're actually at PC? Are there infinite clusters or not? And generally, the belief is that there should not be infinite clusters at PC. But this is a very big problem that's not at all understood, particularly for three-dimensional examples, for example. Ideally, though, we'd like to prove that there are no infinite clusters at PC. And once we do that, we'd like to go further and sort of, can we understand it more quantitatively? If you know that the cluster at the origin is finite almost surely, well, can you describe its distribution? Things like that. And I'll say more about this later. Now, a second question you could ask, which is also very natural, is, well, we know when we're above PC, there's at least one infinite cluster, just by definition. But is there one? Is there three? Are there infinitely many? What can we say about the number of infinite clusters? Now, these questions were traditionally mostly studied in the context of Euclidean lattices, like the square lattice, the cubic lattice, hypercubic lattice. But you can also study all these problems in more general examples. This is something I've been very interested in for a long time. And you get all kinds of new and interesting phenomena by looking at not just percolation, but other kinds of probabilistic processes as well, of course, like random walk in sort of more exotic geometric settings. And so for the purposes of this talk, I'm going to restrict attention to transitive graphs, which are just graphs where every vertex sort of looks the same. So formally, for any two vertices, you can map one to the other by a symmetry of the graph. Okay, so I want to start by talking about the second problem about how many infinite clusters there are. Okay. So in order to study this problem, it makes sense to define a second critical parameter called Pu, which is called the uniqueness threshold. And this is defined to be the infemal P where there exists a unique infinite cluster. Okay. Now, in fact, we have the following kind of general possible phase diagram. So first of all, Newman and Shulman showed in the early 80s that you can never have a number of infinite components that's not 0, 1, or infinity. So it's always one of these three possibilities, and it's not random. The fact that it's not random is just, Kolmogorov 0-1 law. It's classical probability. They showed that it has to be 0, 1, or infinity almost sure. Moreover, in later work of Hagström, Paris, and Shulman, they showed that actually once you're above PU, you really always have uniqueness. In principle, existence of a unique infinite cluster, it's not a monotone kind of thing. So in principle, you might swap back and forth between having one cluster and having infinitely many clusters, but they showed that this does not happen. So in general, you have the pictures shown here but of course, some of these phases could be empty. But in general, you first have a phase where there are no infinite clusters, then you have a phase where there are infinitely many, and then you have a phase where there's uniqueness. And just to stress again, this doesn't tell us that these phases are actually non-degenerate. I mean, there might be no phase where you have infinitely many, for example. It also doesn't tell us what happens at these boundary points. Okay. Now, in the classical setting of percolation on hypercubic lattices, this problem was completely solved in the 80s. So first by Eisenman, Keston, and Newman, and then with a different proof 2 years later by Burton and Keane. In fact, most people now learn the Burton and Keane proof, which is sort of more conceptual. It's a softer argument, but the Eisenman, Keston, and Newman proof tells you a lot more interesting quantitative things, and it's been gaining a lot of traction in recent years, the ideas from this proof. Okay, but they proved that you can never have infinitely many clusters on the hypercubic lattice. So for every P, you either have one infinite cluster or zero infinite clusters almost surely. And the Burton and Keane proof is really, it's one of the absolute classic proofs in the theory. So what they roughly show is that they say, well, suppose you have infinitely many infinite clusters, then you must have these things I have pictured here, which are called trifurcation points. So it's some kind of vertex where if you deleted it, it would split the infinite component that it belongs to into 3 infinite pieces. And then they say, well, if you must have these trifurcation points if you have infinitely many infinite clusters. They argue this by some kind of surgery. You just add some edges, and you can do this with positive probability. And they say, well, because the whole model is invariant under translations, that means that every vertex has the same probability of being one of these trifurcation vertices. So that means if you take a big box, then just by linearity of expectation, the expected number of trifurcations inside the box scales with the volume of the box. Okay, but then it's a combinatorial fact that the number of distinct ways of going to infinity from the box inside the percolation is at least the number of trifurcation points that are inside the box. Okay, that's just a fact about trees. It's not completely trivial, but it's true. And once you have this combinatorial fact, you say, well, that means that, so I've learned that the number of trifurcation points, well, it's at most the number of ways of going to infinity, but that's at most the size of the boundary of the box. Number of ways of going, I mean, you could find a set of disjoint parts that all go to infinity from the box. You can find a set that has size at least the number of trifurcations. But you get a contradiction because the number of trifurcations scaled like the volume of the box, and this number of ways of going to infinity scales at most like the boundary, and that's smaller. So if you take a large enough box, you get a contradiction. Okay, so that's a very brief overview of the proof, but it's a very nice one, and if you're interested, I really encourage you to read a detailed account. So, okay, now what one notices from thinking about this proof is that actually it's not that specific to the Euclidean lattice, and indeed it actually applies to every transitive graph which is amenable. I should say that the Eisenman-Keston-Newman proof also generalizes to all amenable graphs, although it's less obvious. What does it mean to be amenable? Well, it exactly means that I have something that was like these boxes. I have big sets whose boundary is small compared with their volume. Okay, so for any locally finite graph, so locally finite just means that all the degrees are finite, I can define its Chica constant to be the infimum over all finite sets where I look at this, basically the ratio of the size of their boundary to their volume, okay? And if this quantity is positive, I call the graph non-amenable, and if it's zero, it's amenable, right? So Euclidean lattices, like we just saw, are amenable because if I take a big box, its boundary is much smaller than its volume. On the other hand, if I take something like a three-regular tree, it's not too hard to prove that it's non-amenable. There's some positive constant so that every finite set of vertices has boundary at least that constant times its volume. Okay, and as some of you who work, for example, in combinatorics or computer science might be more familiar with expander graphs. Non-amenability is just the infinite graph version of being an expander graph. If you're familiar with expander graphs, you can think of it that way. If you're not, don't worry about it. Okay. Now, one of the biggest problems in this field of studying percolation beyond ZD is this conjecture of Benjamini and Schramm, which says that the converse of what we just saw is also true. So not only should every amenable graph have no non-uniqueness phase, but every non-amenable graph should have a non-trivial non-uniqueness phase. So there should be, in other words, PC should be strictly smaller than PU for every non-amenable graph. Okay, so again, the only open part of the conjecture is to prove the non-amenability implies a non-uniqueness phase. Okay. Now, of course, one example where this is very easy is the tree, because we can compute exactly what PC is using a branching process, and on the other hand, PU is 1 for the tree, because as long as I'm deleting at least some edges, I'm definitely disconnecting my infinite connected components into lots of pieces. So in this example, the third phase, the uniqueness phase, is empty, or it just contains the boundary 0.1. Okay. But on the other hand, you might like to think of something like this example on the left. This is a tessellation of the hyperbolic plane. And actually here, the conjecture is also known to be true, but it's significantly harder. And in fact, here, you really get all three phases. You first have a phase where there's no infinite clusters, then this intermediate phase with infinitely many, and then a final phase where there's uniqueness. Okay. So let me briefly discuss what was previously known about this problem. So really the first paper that really looked at this problem, and before the general conjecture was formulated even, was the work of Grimmett and Newman in 1990. So this was the first example of a graph that was analyzed that really had all three phases. So they looked at the product of a regular tree with ZD. In fact, they were most interested in the case D equals 1, and they called it percolation in infinity plus 1 dimensions. And what they proved is that if the tree has large degree, then you really get all three phases. Okay. Now, once the general conjecture was formulated, most progress early on was of what I'll call a perturbative nature. So the idea here is that we want to prove that something's true for all non-amenable graphs, but what we could do instead is maybe assume something stronger. So non-amenability means that the Chiga constant is positive, but I could assume that it's large or something like that instead. Okay, and there are various variations on this where you assume some strong quantitative form of non-amenability. And then what you can start doing is to try to prove, explicit combinatorial upper bounds on PC and lower bounds on PU, such that if the parameters are all in your favor, then you can just explicitly separate these. Okay, and this has been done, various different versions of this have been done by lots of people. Probably most significant is the work of Pak and Spurnova and Agnabeda. So they proved in particular using these kind of ideas that if you have any non-amenable group, then it has at least one Cayley graph where the conjecture is true. Okay, but these kind of perturbative arguments, combinatorial methods, they're really not expected to be able to handle the general conjecture where maybe the graph is only very weakly non-amenable. Okay. So going beyond these kind of ideas and trying to have the non-perturbative arguments that don't need some parameters to take good values, there are really just two things. So the first is, if you assume planarity of your graph, then you can start playing around with duality and things like that, where you say, well, you know, if I look at all the edges that aren't in my percolation, that's percolation on the planar dual of the graph, and you can start messing around with this, and there's lots of stuff you can do. And indeed, that following partial work by Lally, the conjecture was completely solved in the planar case by Benjamin and Schramm. More recently, I won't go into what this means, but Russ Lyons used this kind of ergodic theoretic property that a graph can have called cost larger than 1 to show that this also implies this. So again, I won't say what this means, but it applies in particular to things which look like the hyperbolic plane but aren't planar, for example. Like if you take the finite range model on the hyperbolic plane. But for example, if you have something that looks like three-dimensional hyperbolic space, then these techniques don't apply. And this is what I want to tell you about today, the new work, which establishes the conjecture for every Gromov hyperbolic graph. So what is Gromov hyperbolicity? Well, it's a notion of negative curvature, essentially, sort of a coarse geometric notion of negative curvature. And what it means is that every triangle should have this kind of pinched shape that you see here on the left. So formally, there exists this constant delta, which, although it's called delta, you should think of as being a large number, such that if you take any geodesic triangle and you take the delta neighborhood of two sides, then it actually contains the third side. So every triangle has to kind of meet together in this sort of tripod shape. For example, if you have a tree, this holds with delta equals 0. Okay, and Gromov hyperbolicity, of course, it was introduced by Gromov, and it's been a massively influential notion. I mean, almost the whole field of geometric group theories seems to spring from this definition of Gromov hyperbolicity. So in particular, it applies to, if I have a graph that is somehow a discrete version of a hyperbolic space, it will certainly be Gromov hyperbolic. So, either a tessellation of the hyperbolic plane, like I have in my MC Escher print here, or in this three-dimensional hyperbolic lattice that I took from Wikipedia on the right here. These will certainly be Gromov hyperbolic. But in fact, this applies to many other things that aren't obviously related to standard hyperbolic space as well. So for example, if you take a random group in Gromov's model of random groups, this will be hyperbolic with high probability. Okay. Now, before I tell you anything more about the ideas going into the proof of this, I want to take a step back and look at question 1 that I mentioned before, so understanding percolation at criticality. And what we'll see is that these two questions are actually very closely intertwined. So just to recap the questions that I mentioned there, the first and perhaps most obvious question that you want to understand about critical percolation is, well, are there infinite clusters at PC or not? Okay, and as I said, in general, this is very hard. But we'd really like to go further. We'd like to not only prove that there are no infinite clusters at PC, but we'd like to understand that various things about the distribution of the finite clusters. So in particular, the kind of the wisdom that we have from the physics literature is that there ought to exist some critical exponents that kind of describe most of the interesting features of these critical percolation clusters. Which is related to this kind of fractal picture that we had before. So just a few examples here. For example, if you look at the distribution of the volume of the cluster at the origin at criticality, it should have some kind of power law, and this is denoted like this. And the most important one for what I'm going to tell you about today is actually this last one, which says that as we approach criticality from below, the expected size of the cluster at the origin should be blowing up. And we predict that it blows up like some power of epsilon, if you're at PC minus epsilon. Okay. So of course, a priori, there's no reason for these exponents to exist, and proving that they exist and computing them, and all these are, in general, extremely hard problems. I mean, for example, for 3D percolation, we don't know how to answer question 1, and there are no guesses about what these exponents should be either. Okay. So one case where we can understand everything very easily and explicitly is for percolation on a tree. And this is because if I do percolation on a regular tree like this, it's exactly the same thing as a branching process, more or less. And of course, understanding branching processes is a classical thing that we teach our undergraduates. And you can compute everything that you want to compute explicitly. And you learn, for example, that the probability that the origin is in a large cluster at criticality is like a cluster of size at least n is like 1 over root n. And that as you approach criticality from below, the expected size of the cluster at the origin blows up like 1 over epsilon. Okay. So what happens for ZD? Well, it's kind of complicated. And actually, it's better to read this slide from bottom to top. So in high dimensions, what happens is that all the critical exponents are actually the same as on a tree. And this is what's called mean field critical behavior. And this was proven to hold, at least for sufficiently large dimensions, by Haar and Sladen. They're very important work in the early 90s. And it's believed to hold all the way down to D at least 7, although this is not being proven. The record now is D at least 11 due to Fitzner and van der Hoste from a few years ago. So that's what happens in high dimensions. And this mean field behavior, where the model behaves in the same way that it does on the tree, is supposed to break in 6 dimensions. So actually, when you're exactly at 6 dimensions, we expect it's almost true, but with some logarithmic corrections. But really, once you're really below 6 dimensions, you expect these exponents are genuinely different. And for example, in 2 dimensions, it's known for a related model for site percolation on the triangle lattice. It's actually been proven that we have all these sort of weird, complicated rational numbers as the critical exponents. And this is sort of the end product of a very important series of work by many people, especially around the early 2000s. And then in between, sort of, if you're in 3 dimensions or 4 dimensions, say, we really don't know how to prove anything at all. But it should be, the exponents should be different than these and different from these. And again, there's no reason to expect that there are any kind of nice numbers, certainly not rational. There's no reason to believe they're algebraic, for example. And even physicists only have arguments for computing the first few decimal places. There's no prediction for what they exactly are. Now, so if you're new to this is all probably quite surprising. What's going on? Why is high dimensions sort of easier somehow? This is a subtle point, and I think it's often explained wrongly. So let me try to give an explanation that's a bit less wrong than you will often hear. So in my view, one important thing that's going on with percolation is that in high dimensions, macroscopic cycles, so loops in the cluster, are not significant, but in low dimensions they are. So for example, here on the left, I have, this is from Gabor Pete's website, it's a simulation of a large cluster in 2D critical percolation, and you see that it has sort of big loops. On the other hand, if you take a large cluster in critical percolation high dimensions, it should look roughly like this thing on the right-hand side, which is the continuum random tree. So of course, the high-dimensional cluster won't literally be a tree. Of course, it does contain cycles, but they should be sort of insignificant at a large scale. And this, obviously, in high dimensions, it's more difficult to form big cycles because there's just so much more space that your parts are less likely to come back on themselves. And this is roughly what's driving this difference between the high-dimensional case where everything starts behaving like it does on the tree, being really genuinely different to the low-dimensional case. Okay. Now, of course, in this talk, I'm not really talking about percolation on ZD. I'm talking about these hyperbolic things. And in fact, in this setting, our understanding is much better in some ways. So in particular, the basic question of whether or not we have infinite clusters at PC is completely understood, basically. So the first big progress here was due to Benjamin, Lyons, Perez, and Schramm in '99, and they proved under this technical condition called unimodularity that holds in most examples, that there are no infinite clusters at PC on non-amenable graphs. And actually, now there are, and this is something I've worked on quite a lot in the past, we have multiple proofs of this, and some of them are more general, and we can get away with a lot less. So for example, we now know that there are no infinite clusters at PC just under an exponential growth assumption, which is a bit weaker than non-amenability. For example, it applies to like lamplighter graphs and things like that. Okay, in fact, even more recently, we've even been able to analyze some examples which have sub-exponential growth, these groups of intermediate growth. Anyway, so the upshot of all this is that this basic question, are there infinite clusters at PC? The answer in our setting is we know that there are no infinite clusters at PC under great generality. Okay. Now, of course, now that we know that, we want to move on to understanding things quantitatively. And here, things are much less well understood. So what we'd like to say is that in this non-amenable setting, where everything's kind of infinite dimensional, we ought to have mean field behavior. So the model should act at criticality roughly as it does on a tree. And this is open, although we do now at least know very generally in this setting that we have some polynomial upper bounds on all these quantities. In fact, the lower bounds of this order hold on every transitive graph, but we have some sort of, you know, with not at all the right constants, but at least some polynomial upper bounds always. I'm not going to talk much more about this. I'll just mention that actually this theorem here ultimately draws quite heavily on the Eisenman-Kester-Newman proof of uniqueness on ZD. Of course, these two statements might seem rather unrelated, but in fact, the proof uses ideas from that paper very significantly. And also just to mention that you know, these results are all about this exotic geometry and so on. But in fact, the methods that I developed to prove this, I've recently been able to use to analyze to get new results back in the Euclidean case, in particular, proving similar polynomial upper bound theorems for long-range percolation on ZD, and also for the Ising model on non-amenable graphs. Okay, so that sometimes, you know, taking a step back and looking at this more general setting can produce valuable insight on the Euclidean models as well. Okay, so the next thing I want to say is try to explain, you know, how does one prove anything about critical percolation? So, you know, many people who come to the model for the first time, will they say, well, I'm going to try to understand percolation in a combinatorial way, where I just sort of count the possible clusters, I count possible boundaries of clusters, something like that. But then they go, well, but I don't know what PC is, and this really throws off a lot of my attempts to do it this way. And these kind of combinatorial arguments, they tend to be useful if you want to understand, when P is very close to 0 or very close to 1. Right? So for example, if you just want to prove that a phase transition occurs, these kind of combinatorial arguments are your friend. And indeed, for example, the Piles argument, which is a famous argument in percolation theories of this form. If you really want to understand critical percolation, though, you need to do something less explicit somehow, and probably of a less counting type flavor. And a way that this is often done is with differential inequalities. So one of the main ones is as following. So for many problems in percolation, it turns out that the key to understanding them is to understand the behavior of what we call the susceptibility, which is just the expected size of the cluster of the origin, right, as a function of P. And it turns out that the derivative of this as a function of P has a nice kind of geometric interpretation where you just say you fix some edge E, and let's call the clusters at the endpoints of E C1 and C2. Then the derivative is, I'm slightly fudging here, but let's imagine this is an inequality. The derivative of the susceptibility is equal to the expected volume of the product of the volumes of these two clusters, given that they're really different. So given that the clusters at the two endpoints of E are not the same cluster, i.e. the endpoints are not connected to each other, what's the expectation of the product? Okay, and this this interpretation is very nice. So in particular, what you can prove is that an upper bound of this form always holds, that the derivative is at most a constant times the square. And basically that's because this condition that the two clusters are not the same is kind of negatively correlated with the clusters being large. So if you impose this condition, the clusters are kind of smaller in distribution than if they were just independent. And of course, if they were just independent, you would get the square here. So this forcing them to be disjoint makes them smaller than if they were just independent. Okay, and once you have this differential inequality, you can do a bit of calculus, and what you learn is that the susceptibility always blows up at least like 1 over epsilon as you approach the critical probability from below. And this just holds for every transit problem. Okay. Now, if you want to establish this mean field critical behavior, so you want to say that the model at criticality behaves in roughly the same way as it does on a tree, then usually the sort of key step that you need to do to prove this is to establish the reverse differential inequality, to prove that this derivative is really lower bounded by a constant times the square of the quantity. Okay, and if you prove this differential inequality, you can integrate it and get an upper bound on how fast the susceptibility blows up as you approach PC from below. And actually, this gives you another kind of window into what's going on in the mean field case. It's basically saying in high dimensions, if I take these two clusters and I condition them to be disjoint, it actually doesn't affect their distribution very much. The space is spacious enough that if I condition on them being disjoint, they don't really care. They don't like to intersect each other that much anyway. So I should get the expectation of this product is roughly the same as the product of the expectations, and that's exactly what I want. Whereas in low dimensions, conditioning it's not conditioning, just multiplying by this indicator is really making them smaller than if they were just independent in low dimensions, and that's accounting for the difference in the two behaviors. Okay. Now, if you want to establish this reverse differential inequality, the hard one that you need to prove mean field behavior, there's a standard strategy for doing this, a sufficient condition that was introduced by Eisenman and Newman in 1984. So they introduced this thing called the triangle diagram, which is this. So you fix some vertex x, and you sum over all vertices y and z of the product of these three connection probabilities. And I stress at this point that this is really a product of probabilities of non-independent events. It's not a probability of three things happening. Okay, and they proved that if this sum is finite at criticality, then you get this reverse differential inequality. And then once you've got that, you can more or less prove most things you want to about the critical behavior. And indeed, this sufficient condition was verified in the work of Haar and Slade to get this mean field critical behavior in high dimensions. Okay, now these non-amenable graphs that we're interested in, well, they're as high dimensional as you possibly can be, so they ought to have this condition as well. So, so the conjecture should be that every non-amenable graph has mean field critical behavior, and this should be witnessed by this triangle sum being finite. But again, non-amenability should be a much stronger assumption than we really need to prove this, but still, it's completely open at this level of generality. I should mention this is also known under these kind of perturbative assumptions that I mentioned before. Okay, and in fact, the proof that PC is smaller than PU for hyperbolic graphs, as I said, this is very closely intertwined with the problem of understanding the critical behavior. And in fact, we also established as part of the same proof that mean field critical behavior holds for these examples. Okay. So in the remainder of the talk, I want to give you a little bit of flavor of some of the ideas going into the proof. And in particular, I'm going to be talking about a new conjecture that I've made that kind of subsumes both of these conjectures that I already told you about. And the idea is going to be looking at things in a certain operator theoretic way. That probably makes it sound much fancier than it actually is. As you'll see shortly, I'm really just going to be looking at norms of certain matrices, but it's a slightly new perspective on the problem, which gives some insight. So first of all, let me just remind you the standard definition. If I have a matrix, so V is always the vertex set of my graph. If I have a matrix with non-negative entries, I can always consider its operator norm from L2 to L2, which I denote this way. Right, this is just the usual definition. Just noting that it's well defined even for unbounded matrices, then you just get that it's infinite, but that's no problem. Okay, so what I'm going to do is I'm going to take my percolation model and consider the matrix where the entry at UV is just the probability that U and V are connected. Okay? And the new conjecture that I've made is that if you have any transitive non-amenable graph, so really this should say locally finite, all these usual things, otherwise things don't make sense, then PC is strictly smaller than this new critical parameter P22, which I define to be the supremal value of P, where this operator of connection probabilities is bounded on L2. Now, for context, if I was instead to look at the operator norm on L1, or equivalently on L infinity, then the norm that I get is just equal to the susceptibility, i.e. the expected size of the cluster of the origin. This is just because if I take any symmetric matrix with non-negative entries, then the L1 to L1 norm is just the sum of the maximal row sum. Okay, so that implies in particular, we know by the classical theory of percolation that PC is exactly where this quantity blows up. So if I was instead to look at to P11, say, that would be equal to PC. But the idea is that if I instead look at the L2 norm instead of the L1 norm, then I should actually get distinct critical values. Okay. So let me, I'll tell you why it's a good conjecture, and then I'll tell you why it's a plausible conjecture, and then I'll tell you roughly how we might go about converting my argument for plausibility into a real proof in the hyperbolic case. Okay, so first of all, as I mentioned, this new conjecture actually implies both the existing conjectures that I mentioned. So first of all, well, if P is larger than PU, if I have a unique infinite cluster, that means that the probability U and V is connected is at least the probability they're both in the infinite cluster, and that's bounded away from zero. And if I have an infinite matrix where the entries are bounded away from zero, then it certainly has infinite norm. And so that means that PU must be at least P22, right? So in particular, if the conjecture holds and PC is strictly smaller than P22, then we must also trivially have that PC is strictly smaller than PU. So the conjecture implies the PC versus PU conjecture. On the other hand, it also implies all this stuff about mean field criticality. And why is that? Well, you've probably forgotten the definition of this triangle sum, but if I were to go back, you'd see that all it is just the cube of this matrix evaluated on the diagonal, right? That was just literally the definition if I wrote it out in terms of matrix multiplication. Okay, and of course, this quantity, the matrix on the diagonal, is bounded by the norm cubed. And so in particular, if you're below P22, then this is finite. So okay, it's a very simple argument. It's telling us that if PC is strictly smaller than P22, then this norm must be finite at PC, and that means that we get that the triangle is finite, the triangle sum is finite at PC, and therefore we get all this mean field critical behavior, and we can understand almost everything that we'd like to understand about critical percolation. In fact, so there are two more reasons why it's a good conjecture. One is that it really gives you something to shoot for. You know, it's more concrete than the old conjecture. So it's nice in that way. It gives you a way of structuring your thoughts about how to solve it. The second thing that's very nice is actually this new conjecture, PC less than P22, it actually has a lot of consequences that don't follow from the old conjectures. So for example, you can compute some critical exponents that you can't, or it's not known how to compute, only assuming the triangle condition. So something I've been particularly interested in recently, for example, is understanding percolation just above PC, slightly supercritical percolation. In fact, under this assumption, we're able to compute all the exponents describing slightly supercritical percolation, which is something that we don't know how to do at all, the Euclidean lattices, except in 2 dimensions. Anyway, so there are many reasons why this would be very nice if it was true. And in fact, it's really the stronger conjecture that we prove in the Gromov hyperbolic case, and which implies these other two conjectures. And just to mention at this point, in fact, I gave a seminar about this at NYU a couple of years ago, but there's another class of graphs where we can also prove the same theorem that the conjecture is true, which is when the graph has what's called a transitive non-modular subgroup. So I won't go into what this means, but one simple example is when you take a product of a tree with something else. So if you take, say, a 3 regular tree, product with ZD. So in particular, this theorem completely solves this example that was studied by Gromov and Newman back in 1990 without needing this large degree assumption. It's a completely non-perturbative analysis. Okay, but I don't want to say more about this. I'm going to focus on this hyperbolic thing. Okay, but by the way, what time should I be stopping? 5:02 or?
I think at the end of the hour.
At the end of the hour, okay. So one nice thing about these operator norms is that many classical arguments in percolation work by studying the susceptibility, right? I already told you, so just the expected cluster size, right? I already told you about this differential inequalities, for example. And I just mentioned that the susceptibility, i.e. the expected size of the cluster, is just the same as the L1 operator norm. But it turns out that many of the arguments that are classically used to analyze that quantity can also analyze the L2 versions of the quantity. And one example here is that, I mentioned before that the susceptibility always blows up at least like 1 over epsilon as we approach PC from below. And in fact, exactly the same thing is true for the L2 norm at P22. So if you're epsilon below P22, this norm has to blow up at least like 1 over epsilon. And this is a very simple proof. I won't explain it because of the time. But it's actually very useful because it means that it kind of gives us an extra epsilon of room. So if we want to prove this conjecture showing that PC is smaller than P22, it seems like we need to prove that this matrix is bounded at PC. But this time it says, well, you don't really need to prove that, because even if you can just prove that it blows up, if the norm blows up slower than 1 over epsilon at PC, well, then PC can't be equal to P22 because the norm is supposed to blow up at least like 1 over epsilon then. Right, so in other words, in order to prove the conjecture, we only need to prove this a priori weaker bound that the norm blows up strictly slower than 1 over epsilon as we approach PC from below. And that's what I just said. So in particular, this leads to a following kind of strategy that we might use to prove the conjecture, but also makes the conjecture very plausible that it should be true. So we can split it into 2 cases. What we can do, we want to show this, that the norm blows up strictly slower than 1 over epsilon. So what we can do is first show that if I instead looked at the L1 norm, that it really blows up like 1 over epsilon. And now this is something that we definitely very strongly believe to be true, because this is just the susceptibility and this thing that it blows up like 1 over epsilon. I mean, that's this classic hallmark of mean field critical behavior. So this first part, okay, it's still difficult to prove in general. We don't know how to prove it, but at least we very strongly believe that this first part is true. Okay. Now, if you were able to prove this, then in order to complete the proof, all you need to prove is that if you look at the normalized matrix, when you divide by this L1 norm, then the L2 norm of this goes to 0 as epsilon goes to 0. Now, this probably seems like a rather weird thing to look at, but something nice is happening because this normalized matrix is bistochastic, right? Because we divided by the row sum. And in other words, it's a symmetric stochastic matrix. In other words, it's the transition matrix of a random walk. And as a probabilist, this makes me very happy because estimating norms of transition matrices, I mean, it's something we have some tools for it. It's something we're used to doing. In particular, we can try using Cheeger's inequality, which, okay, so this theorem has a long history that's rather complicated, but it's a relationship between, if you have any stochastic matrix, symmetric stochastic matrix, so any transition matrix of a random walk, you can always estimate its norm in terms of a geometric quantity, which again is the Cheeger constant, just as we defined the Cheeger constant for a graph before. So this is saying it's the same kind of thing where you're looking at the ratio of boundary to volume, but where you now define the boundary in terms of this matrix. Okay, and we're mostly going to use the upper bound, which is the Cheeger bound. So Cheeger proved this for manifolds, and the generalizations to graphs and other things are due to Doziak and Mohar, and actually many other people have proven all kinds of small variations on this. Okay, so this is something that's going to actually be very useful for us. It relates this norm to something geometric. Okay, and at this point, I have to mention the theorem of Keston, of course, which follows from this, but is also older, which says that it's a characterization of non-amenability. It says that a graph is non-amenable if and only if its transition matrix has norm strictly less than 1. The transition matrix for simple random walk. I'm not actually going to use this, but I can't state this theorem without mentioning Keston's theorem. Okay. Now, so again, what do we want to do, or at least heuristically argue, is I want to argue that this normalized matrix should have norm going to 0 as P goes to PC from below. Well, what happens when P goes to PC from below is that the denominator here becomes very large. So I'm taking this matrix, which is bounded by 1 everywhere, and I'm dividing by a big number. So I get this very spread out kind of matrix where all the entries are very small. Okay, and then this is where it becomes a heuristic rather than a proof. Most examples that you think of like this on non-amenable groups have norm going to 0, right? So just the standard simple random walk has norm less than 1. So for example, one way of generating a spread out random walk would just be to run the simple random walk for a large number of steps. That's certainly going to give you something where the norm is going to 0. Okay, but unfortunately, not every spread out random walk on a non-amenable graph looks like this, right? I mean, you might, for example, have something that is a random walk on a tree, but where there's some like line, like a Z subgroup that you almost always like to walk on. So you might just be very spread out, but mostly concentrated on that, and that would be a problem. Then you wouldn't get small norm. So we need to somehow rule out things like this in the case of this matrix coming from percolation. And currently we don't know how to do that in general. So how do we use hyperbolic geometry? So I've only got 3 minutes left, so I want to skip over that. So there's a theorem of Boncontran that says these hyperbolic graphs, we can always put them inside standard hyperbolic spaces. So for now, I'm just going to talk about standard hyperbolic spaces. And the proof is going to use this amazing, and in my view, highly undervalued theorem of Benjamin and Schramm called the magic lemma, but I think it deserves to be a theorem. And this says that if you take any finite set of points in RD and you look at it from the perspective of a typical element, so a random element, then the set looks like it accumulates to at most 2 points in RD, one of which is at infinity. So for 2 examples, if you took this kind of tube type thing where you have a large number of scales and you have a finite number of points at each scale and you pick a random point in that set, then normally you'll be in kind of a middle scale and you'll see a picture like this where the set kind of looks like it's accumulating somewhere and also to infinity, right? Or if you take just all the points in the lattice and you pick in, not an infinite lattice, but a big box, typically you'll be in the middle of the box, you'll see this kind of picture locally. And it roughly says that these are the 2 kinds of things that can happen. I should mention, although this is also due to Benjamin and Schramm, who are the authors of the conjecture we've been talking about, it comes from completely unrelated work about random planar geometry. So just to give you a more complicated example, suppose I try to construct a counterexample. So I try to arrange my points, maybe so in this dyadic way where they look like they're accumulating at the boundary of the box. Well, if I pick most points here are near the boundary. So if I pick one, say here, uniformly at random, it's probably quite near the boundary. And then if I look at the set from the perspective of that point, so I kind of zoom into that point's characteristic scale, then what I see is this. And this, of course, doesn't look like it's accumulating anywhere except to infinity. And what the theorem says is that something like this happens for every finite set of points. You cannot construct a finite set of points where from the perspective of a typical guy, it looks like it's accumulating more than one place. And what you can deduce from this, just using some trigonometry, is a similar version holds in hyperbolic space, but where now it says that any finite set of points that each have distance at least 1 from each other, say, look like they're accumulating to at most 2 points in the ideal boundary. And so again, I've got less than a minute. So what I'll say is that this tells you in particular, a nice corollary of this is that, so in a non-amenable graph, most points are near the boundary of any finite set. In a hyperbolic non-amenable graph, most points are near the boundary of the convex hull of the set. And using this geometric fact, you can prove this reverse differential inequality. You can also, Cheeger's constant, actually, you can interpret it as something about what finite sets look like from a typical point. And you can, again, use this kind of approximate structure theory of finite sets from the magic lemma to prove something about the norms of matrices, which reduces the problem to just showing that this percolation matrix can't put most of its mass on like one geodesic. This is still hard, but we're able to do it. And sorry for the rush at the end. Thanks very much for coming.